categories.
Okay, so hello everyone. It's a pleasure for me to speak in this seminar for the first time as a speaker. And in fact, I haven't given a talk at Masaryk University since a long time. So it's nice to be back. And today I will talk to you about joint work with P.G. Rosicki.
Sorry.
Yeah, it's fine. Also, this is the first time we have something together with Irji, and so I'm happy also of this collaboration. Yeah. And you can find this preprint on archive under the title Enriched Locally Generated Categories. So what are we going to do today? I will introduce the notion of locally M-generated category, and then we will discuss a sketch-like presentation of those. And then we will generalize this notion to the enriched context. And finally, we will find an application to Banach spaces, which was our initial motivation in this study. Even though I have to say that the theory we developed is much more general than the specific Banach case. Although, I mean, that's really the motivation we started from, so I should say it. So I would like to start from locally presentable category, which is something that people understand a little bit better than locally generated categories. And a locally presentable category is a co-complete category that has a set of kappa presentable objects such that every object is a kappa directed colimit of those. And if you don't like this definition, maybe an equivalent characterization, which is very well known to the literature, is that a category is locally presentable if it is co-complete and has a strong generating set made of kappa presentable objects. So people like locally presentable categories, and there are many reasons for this. One is that there are many examples in nature. Another one is that they are general context, but tame. And the reason for which they are tame is that they allow for example, the small object argument, or for nice versions of the adjoint functor theorem. There are other reasons, but in fact, most of the times you can reduce them to the small object argument. So all in all, they are an efficient framework to do mathematics. Not all mathematics, of course, but a portion of it. And so if you are not super familiar with locally presentable categories, so Irji, in the meanwhile, you can just be distracted if you want. So if you're not familiar, maybe you don't remember the intuition. You have this co-complete category together with a set of objects that you like to think as they were finite. And those finite objects, whatever this word finite means, generate via directed colimits. So maybe a couple of examples, the category of sets, where finitely presentable objects are precisely finite sets, or groups where finitely presentable objects are precisely finitely presentable groups. And then maybe one could say, also Banach spaces. So we could study the category of Banach spaces and one Lipschitz operators. And there is a natural notion of finite object there, which are finite dimensional Banach spaces, maybe. And you would like to say, maybe this category is locally finitely presentable because it is co-complete. Finite dimensional Banach spaces are a strong generating set, So you would like to use the theorem. Although this category is not really locally finitely presentable, because it is not true that finite dimensional Banach spaces are finitely presentable objects. So the Ohm factor does not preserve directed colimits. And so, again, this was our motivation, because in a way, we wanted to acknowledge that finite dimensional Banach spaces are finite, but there was no, there was, in the theory of locally finitely presentable categories, there was no such an option. So, is finite presentability the right notion of finite? Well, definitely it doesn't encompass finite dimensional Banach spaces because they are not finitely presentable, and they are not finitely presentable even from an enriched point of view, whatever that means for the moment. So you open a little bit the literature and you discover that Gabriel and Ulmer didn't just define the notion of locally presentable category, they also define the notion of locally generated category. And so what's the difference? Well, the difference is that an object is locally finitely generated as opposed to locally finitely presentable if the Ohm factor preserves directed colimits of monomorphism. So this notion is more general than locally finitely presentable, because in that case you would preserve all directed colimits, and in this case you just preserve directed colimits of monos. And with this definition in mind, you can give the definition of locally generated category, which is a co-complete category that has a strong generator formed by locally lambda generated objects. There is an additional assumption that is that every locally or every lambda generated object should have only a set of strong quotients. But this can be seen as a kind of technical assumption, and even in some following papers of Iji and Adamek, they tried to avoid this condition. They didn't really, but again, this is a kind of smallness assumption that doesn't play a conceptual role. So locally generated categories are more or less the same or locally finitely locally presentable categories, but we replace this notion of finite. And theorem, a category is locally generated if and only if it is locally presentable. It's not, well, this theorem, maybe one could say that it's Gabriel Ulmer, maybe one could say it's Adamek Rosicki, depending on the formulation and the definition that you choose. And so, but we should be careful because so it's true that locally generated, if and only if locally presentable, but when you try to check the lambda, every locally lambda presentable category is locally lambda generated, but the vice versa is false. So you shouldn't expect that a locally lambda generated category is locally lambda present. And so, long story short, the two frameworks are essentially equivalent, but they are not equivalent on the nose, so not for the lambda, for the same lambda. Okay. So, okay, back to Banach spaces. So in the case of Banach spaces, Adamek and Rosicki proved in 2018 that a finite dimensional Banach space is in a sense finitely generated, in the sense that the enriched factor, which goes from Ban into CMET, preserves directed colimits of isometric embeddings or isometries. So that's a good news, because they are finite in a sense, although we don't see any more monos here, we see isometries. And this is good because isometries are kind of monomorphism, at least also in a technical sense, but especially from the point of view of the intuition. And then we see the word enriched, which was not there before. So the notion of Gabriel Ulmer was not developed in the enriched case. So if we want to get some theorem about Banach spaces, we really should extend the theory of locally generated categories to more general classes of monomorphisms. And then we should also enrich it. So that's the first part of what we did with PhD. And so we say that a category K so let's look at the definition of locally generated category. Of course, in this definition, you will see some notions that I haven't introduced to you, but I will introduce to you in a moment. So the definition we came up with is that a category is K co-complete is locally lambda generated when it has a lambda convenient factorization system, and there is a set of lambda generated objects with respect to this factorization system, such that every object is a lambda directed colimit of those. Again, I didn't really define all the stuff here, but let's try to understand what I need to define. I should tell you what is a lambda convenient factorization system. And of course, here monomorphism will play the role of M. Then I should tell you what means to be lambda generated with respect to such. And then that's it. That's more or less what's missing to understand this definition. The rest is very similar to locally presentable. So a similar notion was already discussed by Adamek and Rositsky. I don't want to say in what it was different because it would become too technical. So in order to understand this definition, I should tell you what is a lambda convenient factorization system and what means to be lambda generated with respect to it. Okay, we can do that. So what is a lambda generated object with respect to M? So when a category has a factorization system EM, we say that an object is lambda generated with respect to it when the OM functor preserves lambda directed colimits of M morphism. Of course, when M is everything, you recover the notion of locally, of finitely presentable. And when M is monos, you recover the notion of the classical notion of generated. So this notion is more general and encompasses all the notion of finite that we know. And then what is this notion of convenient factorization system? So given a factorization system and a category, we say that it is lambda convenient if it is co-well powered, and this corresponds to that assumption I mentioned before, that strong quotients had to be a set. And here again, the E quotient should be a set. Then M should be closed under lambda directed colimits. And to be precise, this means that a colimit co-con consists of M morphisms. Oh, sorry. And for every co-con, the factorization is still in M. So, okay, this notion of convenience, at the end of the day, the important part is just that M is closed under lambda directed colimits. That's what one should remember of this definition. And I'm not saying that the assumption number one is not important, but I cannot say that it is conceptual. Okay, so we have enough ingredient to understand this notion, and let's read one last time the definition. The definition is just saying that we have a co-complete category with some notion of monos, which is this factorization system, and then some small objects with respect to the monos that generate everything under directed colimits of monos. So let's see a couple of examples, even though I already mentioned some examples in a way. So we can take the factorization system every map and isos, and an object is lambda generated if and only if it is lambda presentable, of course. And then we can choose the opposite factorization system, and in that case, every object is lambda generated. And then we can choose the factorization system strong epi mono, and in that case, lambda generated is really the notion of Gabriel-Ulmer. So let's see some examples of locally generated categories. Okay, the first example, I already mentioned it. This is the case of locally presentable categories, which are generated with respect to isos. Then we have also a pathological example, which is that K is iso locally generated, if and only if it is small. So I think this shows that this notion really can become strange under some when the assumptions are not natural in a way. And then the notion of mono locally generated is the one that was studied by Gabriel and Ulmer or by Adamek and Rositsky in the classical literature. Okay, so the first part of what we did with Hirschi was essentially to generalize a little bit the notions that were already in the literature. And then the first good news is that we managed to recover this theorem 1.11, that is that a category, a co-complete category equipped with a lambda convenient factorization system is locally generated with respect to the factorization system, if and only if it has a strong generator formed by lambda generated objects with respect to M. Again, this is really in complete analogy with locally presentable categories, and it's an easy to check way to prove that a category is locally generated. Because it's very easy to show in general that a category is co-complete, and then you just need your factorization system to be, say, stable under directed colimits of monos, which happens very often. And then as soon as you find a generator made of small objects, you are done. And another theorem in this direction is that when you start from a category of this kind and you have a monad over it, if the monad preserves directed colimits of morphisms in M, then the category of algebras will still be locally lambda generated. Here, I'm cheating a little bit, but the statement that you find on the screen is correct, because in order to make this theorem work properly, you have to assume Vopienka principle. Well, you have to, not really. We just have a proof in the case in which you assume it. We don't know whether you can remove it. Maybe you can, maybe you can't. We definitely know that if you manage to remove the assumption of Vopienka principle, you also solve another open problem that Hirschi and Hirschi had left in the past. So definitely it is not trivial how to remove Vopienka principle from this theorem. So long story short, we have an easy way to check that a category is locally generated, and then we know that locally generated categories are closed under some constructions. For example, taking algebras for nice monads. Of course, the monads must interact nicely with the factorization system, otherwise you have no chance for such a result. Okay, so we introduced the notion of locally M-generated category, and this was the first step. And now we still have some stuff to do here, because we should discuss a sketch-like presentation of those, and then again, we should move to the enriched context, and then we should find some application to Banach spaces. Don't worry, the worst was this part. So don't expect that we have to do 3 times what we already did. So from a logical point of view, we move to axiomatization. And some people like to say that locally presentable categories are axiomatized by essentially algebraic theories. Of course, I'm one of these people. But some other people prefer to say that they are axiomatized by finite limit theories, or sketched by finite limits sketch, or from a semantic point of view, you can say that they are, or if you are really a category theorist, you can say that they are captured by finite limit, finite limit categories with finite limits. Yeah, it's right. Or finally, if you think very semantically, you can say that they can be reconstructed from their presentable objects. So it really depends on your background to say which one of these statements you prefer. But in a sense, they are all the same statement. And if you want to synthesize this result, the motto is that categories with finite limits offer a categorical presentation of essentially algebraic theories. And from a quantitative point of view, the theorem is that when you have a locally finitely presentable category, this is the category of Lex functors from finitely presentable objects into set. And notice that this statement makes sense because K omega is a category with finite limits. Otherwise, the previous, otherwise, where is the finite limit sketch, or where is the category with finite limit in this statement? So all in all, this means that you can use finite presentable objects in order to axiomatize your category, your finitely presentable. And what we wanted with Hirschi was a similar result for locally generated category. And so we had to come up with a notion similar to the notion of finite limit sketch, or the notion of category with finite limit. And this is the notion of nest. So what is a nest? A nest is a category C together with a factorization system such that C has small lambda limits. So of course we can think about the finite case, so say finite limits. And then you need multiple pullbacks of M morphisms. So this notion is maybe a bit confusing. Maybe people don't know what is a multiple pullback. And so I prepared a slide to introduce them. So a multiple pullback is a limit consisting of morphism of this kind, a limit of a diagram consisting of morphism of this kind, such that P is obtained by iterated pullbacks along this morphism. So this is explained a little bit better by this diagram. So you take P0, and then you take P1 along P0, and then you just proceed by recursion, and at limit steps you take limits. Of course, with this kind of argument, we also gave another way to present multiple pullbacks because they can be seen as limits of smooth, well-orderable chains. And one can show that this is kind of an if and only if presentation of multiple pullbacks. Okay, so back to the definition of nest. It should look similar to the notion of category with finite limits. Of course, when I say finite, it works the same for the lambda case. So that's why I mostly concentrate on the finite one. And this notion of pullback is just a nice compatibility with the factorization system. So when you have this notion of nest, you can define the notion of model of a nest. And this is just a functor preserving lambda small limits and multiple pullbacks of M morphisms. And the theorem here is that when you have a M locally finitely generated category, if you restrict to the opposite of the category of models, this is an omega nest. So in the same way, when you had a locally finitely presentable category, K omega was a category with finite limits, K omega op. In the same way, K omega op is an omega nest. And the factorization system is essentially the restriction of the factorization system of K, and then you take the opposite. And you can show that this has multiple pullbacks. If you want to be convinced of this, so very often finitely generated objects are closed under strong epis, for example, if you are used to the classical theory, and then when you take the op, this becomes that you are closed under pullbacks in this sense. And the theorem here, which is the same characterization result we were hoping for, is that if K is M locally finitely generated, then K is precisely the category of models of the nest associated to its finitely generated models. So we can use nests as a new notion of sketch, and so as a new notion of theory, even though we don't know yet, or we will never know, who knows, what kind of logic this notion of nest axiomatizes. Because definitely this is more expressive than essentially finitary, essentially algebraic theories. Okay, so we have this result. And in the paper with Irgi, here I don't want to go too much in the detail, we offer a complete Gabriel-Ulmer duality. So this is for people that know what is Gabriel-Ulmer duality, you really can expect the statement. And for people that don't know what it is, it would be too hard to introduce it here. But once you have this result, Gabriel-Ulmer duality is essentially proved. You still have to say something about the morphism of these structures, but the hardest, the most conceptual part is already done. Okay, so I think we did the first two steps. We introduced this notion of locally M-generated category, and we discussed the notion of nest that helped us to axiomatize them. Now we should say something about the enriched case. So in order to make sense of this, we should speak about the notion of enriched factorization system. And this notion exists in enriched category theory, although just for today, I will not give it in full generality. What I would say is that for us, an enriched factorization system on a category K, which is enriched over V and tensored over V, is nothing but a factorization system over its underlying category, such that E is closed under tensors. And so we can think about factorization systems in K just as factorization systems in the underlying category, such that the category of epis behaves nicely. So our intuition can be not too enriched in a sense. And in the paper, we only discuss this case because in all the examples we have, this is verified. It is verified that K is tensored over V. Well, K has all colimits, all enriched colimits, in fact, in our case. And then I should tell you what is a convenient enriched factorization system. Oh, here there is a typo. I'm sorry for the typo. But of course, the notion now is just that the underlying factorization system is convenient, which, just to remind you, again means that the class of monos is closed under directed colimits of maps in M. And again, I should tell you what is a lambda generated object. And the definition is precisely what you expect. We want that the enriched Ohm functor preserve directed colimits of M morphism. So really the definition, once you observe that factorization systems behave nicely, and this result was mainly done by Lucy Sheen Wright, the generalizations are quite straightforward. And so is the generalization of enriched locally generated category, which is that a co-complete category K with a lambda convenient enriched factorization system is locally lambda generated if you have such a generating set of lambda generated objects such that every object is a lambda directed colimit of objects in A and morphisms in M. Unfortunately, the definitions become a little bit technical now, and I know it, and no one likes it. But the intuition is very simple. We are just taking the definition of locally presentable category, and we are making more general the notion of finite object, and then the rest is really the same. Okay. And so we can show a couple of theorems about these categories. And the first one is this way to check when a category is locally lambda generated. And the theorem sounds as expected. It is a co-complete category equipped with a lambda convenient factorization system that has the proper notion of strong generator. So you really manage to recover the theorem you want. Although notice that in order to make this theorem work, you have to assume that the base of enrichment is locally lambda presentable. Otherwise, you don't get such a result. So this word of locally generated categories, enriched, in order to work, need that the enrichment base is as locally generated as possible, which means to be lambda presentable. So the notion of locally generated for the enrichment base must be the most rigid one. Now, what you manage to do is to develop a notion of enriched nest. I don't want to give the definition here because it's the same definition of before, just you put the word enriched and it really works.
Ivan?
Yes.
Can I ask, just to be clear, is a nest supposed to be small?
Okay, good question, thank you. So we study only the small case, yes. Although, of course, you can give the non-small definition and you can study models, of course, but and you will get a nice theory. Eh? I'm not saying you will not, but if you look at this from the point of view of Gabriel-Ulmer duality, it's more natural.
That's what I was asking, yeah.
Although, I mean, the theory you will get for large nest is still quite interesting. Just you will have to be careful with size issues here and there. This is the same that happens for locally presentable categories after. Again, under the assumption that V is as nice as possible, you manage to recover the reconstruction theorem I was mentioning, which is that K can be seen as enriched models over its lambda generated objects. Again, in the preprint, we go much farther than this, and we really develop the full Gabriel-Ulmer duality. But I didn't really want to I didn't want to introduce here the notion of morphism of such categories, even though it's very natural notion and it's a kind of Quillen adjunction that behaves nicely with the factorization systems at the end of the day. But what matters is that under the hypothesis that V is locally presentable as a monoidal closed category, you manage to recover the reconstruction theorem you were looking for. That is that K is the category of models of its nest of finitely of lambda generated objects. Okay, so we managed to generalize this theory to the enriched context, and now we should say something about Banach spaces. But maybe we did everything. Did we? Let's check together. So let's just put this theorem here. The theorem, it's a theorem I already announced, which is a way to check that a category is locally generated. And it's a successful result because it's enough to check that you have this strong generator and then everything will work. So back to Banach spaces. So Banach spaces are enriched over this category, C-met. This is the category of complete metric spaces and non-expansive maps. This category is monoidal closed. This was shown by Rositsky and Tolle. So this is a check, I would say. We have our V. Then Banach spaces have a factorization system, which is given by dense map and isometries. This is also good news. And this factorization system is finitely convenient. So, okay, we are in a good path. And then there is the result I started with by Rositsky and Tolle, that finite dimensional Banach spaces are a strong generator in this category, which is made of objects which are lambda generated with respect to, sorry, this shouldn't be a lambda, so finitely generated with respect to isometries. So it looks like we have all the ingredients we need. So is Banach spaces locally finitely generated? Well, there is a problem here that I've been mentioning all the time, that you need V to be as finitely presentable as possible in order to make this work. And so there is an issue. The issue is that C-met is not finitely generated as a closed category, so we cannot apply the theorem. The good news, although, is that if you just believe in the theorem very strongly, you manage to prove it. And the result is that Ban, as an enriched category over C-met, is locally finitely isometries generated, and it is axiomatized by the nest of finite dimensional Banach spaces. The way you get this result is that you define the nest, and then you have to check it explicitly. And of course, this needs a little bit of knowledge of Banach spaces. And the theorem cannot be trivial because, again, complete matrix spaces are not a very nice enrichment base. So I have to say I'm finished, but before finishing completely, I would like to make a couple of comments. So together with Hirschi, we are looking for more examples of these enriched locally generated categories, even not enriched. And recently we think we can do something with topological spaces generated by compact ones using closed embeddings as monomorphisms. And although we don't know other examples, and we would like to know them. Also, another thing we don't know is whether, given any locally presentable category, we can find a factorization system such that it is finitely generated with respect to it. we don't really believe this to be true, but if it is true, it would be very nice. It would be surprising, I would say, more than very nice. Okay, so I will stop here, and if you have questions or comments.
Okay, thanks, Stephen, for a nice talk. So, silent round of applause, and then, yeah, feel free to ask any questions.
So I was thinking about the logic axiomatized by the nest that you mentioned. So if you can remind me again the definition of a nest, it has lambda small limits.
I will go to the slide. Okay, it has lambda small limits and a factorization system.
Okay.
And
so
then
you require the multiple. This multiple pullbacks is the same as wide pullbacks, right?
I don't think so. Maybe if she wants to comment on this, but I wouldn't say so.
It's
yes,
not the same.
Wide pullbacks, and if you do it, say on the dual, say it's something like you have these junctions over those epi which correspond to multiple push-outs.
Sorry, again.
Yes, that should be something that you have, that you allow some infinitarious junctions. These junctions corresponds to push-outs of
Yes.
Of that, yes.
Yes.
So of course, but these are finite. So you have something like finite limit theory with a kind of, say, infinite disjunctions. That would be how it should look like, yes.
But we don't know which kind of disjunction you can do, because you don't have any kind of this.
Yes. So that's.
So it's a kind of Horn theory, the way I understand it, but we don't know precisely what kind.
You see this concept of a lambda nest is in Gabriel Ulmer in the case that you take a strong epimono. So they have this kind of theory in some sense when you have these multiple push-outs of strong epis. But as Ivan told, so this is not a real, say, precise logical description of this.
Can I just ask about, so when you have your full Gabriel-Ulmer duality for this sort of setup, do you have it as an equivalence of two categories, or?
Yes, a biequivalence of two categories.
Okay, and is that's a sort of dualization induced by a dualizing object?
Yes.
Okay, so yeah, so that doesn't require Vapenka's principle, does it?
It does not.
Yeah, okay. No, just I'm curious because...
But in order to make it work, you need V to be locally presentable, because this is the dualizing object. It's V together with the structure that makes it generated.
So, John, this dualizing object, that should be set, yes? But there is a large nest. So if you would like to have it via dualizing objects, then you would go to something which one can call class locally generated categories.
No, I think I understand. I guess I'm thinking of the large case, and then you restrict, like in the classical setting. But so my only question was, the reason for my question is that in the classical case, you have an equivalence between small categories with finite limits on the one hand, and locally finely presentable and limit-preserving filtered co-limit preserving functors on the other. So a nice way of proving the limit theorems for locally presentable categories is to observe that the two category of small finitely complete categories has bico-limits. And then since you have a biequivalence, so does the two category of locally finally presentable categories. And so that actually is equivalent. It implies, because the adjunction commutes with the forgetful functors, it implies that that the two category of locally finitely presentable categories is closed in cat under pi limits and things. So I'm just wondering, in your case, whether you could deduce the result that if you have a monad which preserves directed colimits of M sub objects, then its category of algebras is locally generated. If you could show that the two category of nests was bico-complete.
This is a question I had myself, and I don't remember if we discussed it with Irji, but definitely what you are saying is essentially to import the standard result of having bilimits for LP to this context. And definitely, I don't know whether it can be done, to be honest.
No, John, yeah. you can take idempotent monad, yes? Which means that in fact you take full arithmetic subcategory closed under lambda colimits of M-morphisms. And the question whether it is locally presentable is not known even in Gabriel Ulmer case. So that's one of problem Ivan mentioned, that you can do it under Vopenka's principle, which exactly shows you that your category is locally presentable, then you get it. But that's not clear. So this is the open problem. You have a locally presentable category. You take its full arithmetic subcategory, close and colimit of monos. So is it locally presentable?
Yeah.
So it seems that this is, and the problem is with this covert poweredness, in fact, which this is there, yes.
Okay. So, I'm not sure I fully I think it feels to me like it should follow formally from the Gabriel Ulmer duality, but I must be missing something.
No, notice that here, in order to make what you said meaningful, at least from my understanding, you should show at some point that the category of nests has some limits or some colimits.
I will know exactly. I mean, what I'm saying is that if you could show that the two category of nests had bicolimits.
And this is something that, and so to answer to your question, this is what we don't know.
Okay, good. yeah, that makes sense then.
And then, of course, if you show such a theorem, then you propagate it as you were mentioning. But
yeah,
we just don't know.
This is a very good point. So in fact, one should, Ivan, that's a good point. Yes, this comment. Yes, because in some sense it's more general. This monad case, you can ask about some kind of good weighted limits. Yes.
Okay.
Yes.
And maybe a final remark then. So my last comment about why it's easy to show, for example, that the two category of small categories with finite limits has bicolimits is that you can express them, for instance, as the algebras for a two monad on cat. So I don't know. I mean, maybe, so you probably can't, it's probably not so obvious that you can express these nests and things in that way. So as algebras for some sort of.
So one part of this is that, of course, the categories with finite limits are monadic,
yeah.
And also categories with a factorization systems are monadic. And then you should hope for a kind of distributivity law between these two monads and hope for the best. Yes?
Yeah, but it sounds plausible.
I just don't know.
So, but anyway, yes, so that was just I just thought I'd mention that sort of thing. So thanks for that. Any other questions?
Sorry, if I can still make one remark, I wanted to say that this notion of nest, appeared in different ways in the literature, where in higher generality has the notion of category with display maps, which was introduced by Taylor. I mean, that notion is definitely more general than our. Although it is really in the same spirit, especially the notion of model of category with display map is very similar. And so, like, some variations of this concept have appeared, even though this version didn't really. And they have some, like the type theory that is related to this display maps is understood. So the logic that these categories should axiomatize should look like the type theory that axiomatizes categories with display maps.
Okay, any further questions? Well, if not, then let's thank Ivan again for a nice talk.
Thank you.
Okay, and so that's it for today. We can stop recording.